Guys, Mr. Carlson here again, and in this video what I want to talk about is the natural abundance of isotopes and also show you how to calculate the average atomic mass of different elements. In last week's video we were talking about basically just the basics of isotopes. How do we write different isotopes? How do we figure out number of protons, neutrons, the charge, all those different things. Um, Today, what we're going to do, so natural abundance of isotopes. Now, what do I mean when I say the natural abundance of something, the natural abundance? Well, natural meaning what we would find in nature. Okay, that's what I mean by natural, what we would find in nature. And then the abundance meaning how much of it, how abundant is it. So when I say the natural abundance of isotopes, we're looking at the different isotopes of an element and we're seeing how much of it do we find in nature, essentially. So again, last week we were talking about how we've got these different versions of elements. So in other words, not all atoms of an element are exactly the same. So if I were to look at, let's say, hydrogen, for example, we would see that not all atoms of hydrogen are exactly the same. I could find, for example, some atoms might be H1 atoms. In other words, atoms that only have just one proton. I could also find atoms of hydrogen that are H2, meaning they have one proton and one neutron. And then I could find H3 atoms, which is one proton and two neutrons. So again, what we saw last week was we've got these different versions of hydrogen, okay? And the way that they're different is they can have different numbers of neutrons. They all have one proton. That's what makes them hydrogen, is the number of protons that they have. But they can differ on how many neutrons they have, okay? So we've got these different versions of hydrogen, and what we're going to see today is that these different isotopes have different abundances. For example, hydrogen 1 here is way more abundant. We would find hydrogen 1 way more often than we would find hydrogen 2 or hydrogen 3. Like, for example, if I were to go outside, okay, and I were to collect some air from outside, let's say, and let's say I was able to just collect just the hydrogen gas that's in the air. Let's say that I was able to easily do that. I could go outside and I could pull a large sample of hydrogen gas from outside. And let's say I could put those gas particles, okay, in this container. And they're all just hydrogen molecules in there floating around in this container, okay? What we would see is that, again, some of these hydrogen atoms that are in here, some of these hydrogen atoms are H1 atoms, some of them are H2 atoms, and some of them are H3. But here's the thing. We would find more often than not, pretty much most of these atoms are going to be H1 atoms, and a very, very small percentage of them are going to be H3 atoms, okay? So the abundances of these isotopes are not equal. It's not like I'd find equal amounts of H1, H2, and H3. It's not like it'd be like 1/3 is H1, another third of it is H2, and another third of it is H3. No. What we would see is that most of them are H1, and maybe a few of them, if any, are H2 and H3 in here. And so that's what we're talking about when we're talking about the abundances of isotopes, because that's the same thing for any element that we see on the periodic table. So for example, here, let me erase this. Let's do an example of potassium. So if I were to take let's say I were to take a banana, okay? If I were to take a banana, which bananas have a lot of potassium in them. Let's say I were to take all the potassium out of that banana, okay? If I were to take all the potassium atoms that are in that banana, if I were to take them out and I were to analyze the different isotopes that are in that potassium, I would see that 93.26% of those potassium atoms that were in that banana, 93.26% of them have 20 neutrons. I would see that about 6.73% of those potassium atoms have 22 neutrons. And then I would see that 0.01%, so very small percentage of those potassium atoms would have 21 neutrons, okay? Now, again, they're all potassium, okay? So let's say I want to write the isotope symbol here for each one of these. They're all potassium, and if I go to the periodic table, potassium is 19. So all of these isotopes have 19 protons. Okay, so if I were to write that, they each have 19. Whoops, I wrote that wrong. Look at that. Even Mr. Carlson makes mistakes. So they each have 19 protons. But they have different numbers of neutrons. So remember, the mass goes up here in the upper left-hand corner for each of these. So 19 plus 20, that's going to give me 39 for a mass for this one. So for K39 here, for this isotope, that's the most abundant one by far. So if I were to look at all the potassium atoms in that banana, 93% of them are going to be K39. So more often than not, I'm going to find this isotope of potassium. That's the most abundant isotope in nature for potassium. The next most abundant one would be this guy here. So 19 plus 22, that's going to give us 41. So for K41, for that isotope of potassium, it's 6.73% abundant. So 6% of the time, it's going to be K41. And then the very smallest abundance here is going to be this isotope. So 19 plus 21 is going to give us 40. So for this isotope of potassium, for K40, we're barely ever going to find this, right? This is 0.01%. It's almost nothing. So basically, almost a very, very small amount of that potassium in that banana is going to be this guy. And most of it is going to be this isotope here. And here's what's interesting is, see, if we were to look at that would be from just like one banana. But if I were to take if I were just to pick another random banana out of that stack, okay? Take another banana and I were to analyze the potassium in that banana, we would see the same percentages of potassium in that banana. Or if I were to go and dig in the ground and let's say I just, for some weird reason, happened to come upon a chunk of pure magnesium metal in the ground, we would see, if I were to analyze it, this would be the abundances of those different isotopes within that chunk of magnesium. So in other words, these percentages for these abundances of these isotopes of potassium, this would be the same for any sample of potassium that we find. And that's what we mean about natural abundance. So any sample of potassium that I find in nature, it's going to have these percentage abundances for each of those isotopes. Okay? Now here's the thing. So here are the masses, right? I've got a mass of 39, I've got a mass of 41, and I've got a mass of 40. Okay, those are the different masses that I can have for potassium. But if what do I write then on the periodic table? Because again, if I look at the periodic table, right? The periodic table lists two numbers. It gives me the number of protons and it gives me the mass, which is how many protons and neutrons added together. But if you notice that pretty much all of the numbers for the mass for each element on here, it's a decimal, which doesn't make any sense, right? Because we just said that the mass is you're just adding up this with how many protons, so it should be a whole number, right? It should be a whole number. Why are all of these this kind of decimal? And the reason being is because all of these elements on here, they have different isotopes. And so what you have to do is you have to take the average, of these masses to list on the periodic table. Because not all potassium atoms have a mass of exactly 39. Some of them have a mass of 40 and some of them have a mass of 41. But now here's the thing. If I were to take an average of these though, so if I were to take an average of 39, 41, and 40, right? So if I were to just do a regular standard issue average, 39 plus 41 plus 40, okay, if I were to add those up, so I would get 120 and divide by 3, because that's how we're going to find the average, 120 divided by 3, it would give me 40. Well, how come then, if that's the average of these masses, right, why don't I just put 40 then for this right here? Why is it 39.1? That doesn't make any sense. 40 would be the actual average of those three different isotopes. And the reason is this. Think about this for a second. Yeah, that's the average. Okay, that's the average. If I were to just take these three numbers, add them up, divide by 3, that's the average that I would get. It's the middle, right? But here's the thing. We just got done saying that 93% of the time, I'm going to find K39, right? That's my most abundant isotope by far. So this number really doesn't correctly represent how often I would find this number, right? So yeah, that average would be 40, but I'm not going to get this. I mean, look at potassium 40 is 0.01%. That's basically nothing. So more often than not, I'm going to find it as K39 than I am as K40. So this really isn't a good representation of that. And so what we have to do is, instead of doing a regular average, we have to do what is called a weighted average. Weighted average. Basically, we have to assign each of these masses a weight according to how abundant they are. So this one right here definitely holds the most weight because it's 93% abundant. Okay, this one would hold the next to most amount of weight, and then K40, which would have been our regular average here, holds the least weight because it's barely anything. We would barely ever find K40. It's a very rare isotope. And so the way that we would find the weighted average, again, we're just going to assign a weight to these different masses. So here's how we would do this. So weighted average, or I'm going to label this, or how to, we'll say calculate the average atomic mass. So let's say I wanted to calculate the average atomic mass for potassium, okay? The way that we do that essentially is what we're going to do is we're going to take the mass of one isotope, okay, so mass of just one isotope, and we're going to multiply it by the percent abundance of that isotope. And we would do that for each isotope. So for potassium, there's 3 different isotopes, so I would have to do the mass times the percent abundance 3 times. Mass times the percent abundance. So mass of K39, the mass of K41, and the mass of K40 times the percent abundance of each one, and that would give me, and then I would have to add all those together, and that would give me the average atomic mass. So let's just do that right now. So I've got, let's take a look here. So I've got 93.26% of K39. Okay, so I'm going to write the mass, which is 39, multiplied by the percent that I find that one. So the percentage of time that I find that is 93.26. So I'm going to put that in as 0.9326. Because when we're multiplying by percentages, we're going to move that decimal 2 places to the left there. And then we're going to do that for each one. So then for the other 2, I'm just going to leave this right here. So for a mass of 41, multiply that by, move that decimal 2 places, 0.0673. And then the final one there, potassium 40. We find that only 0.01%, so move that decimal again 2 places, 1, 2 to the left, so that's going to be 0.0001. So I'm going to multiply these through, so it's going to be 39 times 0.9326 would give me 36.3714. 41 times 0.0673. I got to do that one real quick. 41 times 0.0673 gives me 2.7593, and then 40 times 0.0001 would give me 0.0004. So again, you can see how this one basically isn't really 0.0004 is basically nothing, right? So most of the weight, again, is with this one right here, which makes sense because I find that one 93% of the time. And so now all I have to do, once I've got my weights there basically, I just have to add them together. And if I add them together, let's see, 36.3714 plus 2.7593 plus 0.0004, and I get 39.10, and that is the average atomic mass of potassium, which again makes sense because that's what we see right here. And that's the process that you would have to go through to find the average atomic mass of any of those elements. Okay, so if I had to figure out the average atomic mass of, let's say, chlorine, this is what you would do. You would take the different isotopes of chlorine. There might be more or less than 3, but you'd have to take the isotope, the specific isotope of chlorine, multiply it by the percent abundance, and then you do that for each isotope. You add them all up, and that's the average atomic mass. Average atomic mass. And we should say the average atomic mass that's on the periodic table. Okay,